Hi, I'm Peter Clark, and I'm going to talk about our work on a system called RuleTaker, in which we train transformers to reason over rules in natural language. This is joint work with Øyvind Taffert and Carl Richardson at the Allen Institute for AI. So it's been a long-standing goal of AI to build systems that can reason, in other words, draw valid conclusions given some facts and rules. This goes right back to McCarthy's advice taker system in the 1960s. But using formal logic for this has proved challenging in AI. Formal systems are hard to build and their behavior is often very brittle. So in this work, we're exploring a modern approach to this and asking whether we can train models to do this kind of reasoning, but using theories expressed in natural language rather than logic. For example, consider this simple description of a circuit. I describe a circuit here. A circuit has a battery, the circuit has a light bulb, and then I have some general rules about electrical circuits. If a circuit has a battery, then the circuit is powered. If a circuit is powered and has a light bulb, then the light bulb will glow. And we want to ask here, will this particular light bulb glow? And a system that can reason with these rules should come up with the answer true. And so our question here is, can transformers learn to do this kind of systematic reasoning? And this is quite a different task to the typical question answering task studied in NLP of QA as span prediction, where we find an answer in a passage of text. Instead here, we're wanting the system to reason with a set of rules that it's been given. And it's also quite different to the task of inducing rules from lots of examples, something that transformers are already known to be very good at. For example, we don't want to give the model hundreds of examples of circuits and have it learn that if there's a battery, then the circuit is powered. Instead, we just want to tell the system that fact explicitly in a single sentence and have it reason with this appropriately. So can transformers learn to do this? So to kind of give the answer ahead of time, the answer is yes. And I'm going to first give you a quick demonstration of RuleTaker so you can see the result. I'll then describe how we build RuleTakers and the experiments we conducted with them. So what I'm going to do here is type in some facts and rules into the system. So first of all, I type in metals conduct electricity. Insulators do not conduct electricity. Then I'm going to tell it some facts about nails. Nails are made of iron. Iron is a metal. And now we can ask a question. So is it true that nails conduct electricity, given these facts and rules that I've given it? If we click submit and ask the question, RuleTaker correctly comes back with the answer true. So evidence it's using these rules systematically. Suppose we now change this and say iron is an insulator, and now we ask do nails conduct electricity? RuleTaker correctly says false. Suppose we change it to say, well, nails are made of plastic, and plastic is an insulator. Again, ask the question. Again, RuleTaker produces the correct answer, false. And suppose we add in a counterfactual, plastic is a metal. And now we ask the question. Now again, RuleTaker correctly says nails conduct electricity. And RuleTaker is robust to fairly different phrasings. Suppose I rephrase that first sentence as metal objects conduct electricity, we get the right answer. If I rephrase it again as if something is made of metal, then it conducts electricity. And now we ask the question. Again, the system comes up with the answer true. And just to show it's not queuing off the word conducts, if I change this to doesn't conduct and ask the question, again, RuleTaker produces the correct answer false. So this illustrates RuleTaker reasoning systematically with the rules and facts I give it, and its robustness to different phrasings. And you can see the URL here at the bottom to try this out. So how do we build RuleTakers? We need to supply it with some examples of the reasoning that we want it to perform. For example, one training example might look, metals are magnetic, nails are made of metal, and then I have a question, nails are magnetic. And given this information, the system should produce the answer true. And another answer might look as follows. Metals are not magnetic, so a counterfactual here. Nails are made of metal. And then we're going to ask the question again, nails are magnetic. And given this particular set of facts and rules, we'd expect the system, or we desire that the system will produce the answer false. So these would be two examples. How can we generate such examples at scale? Well, we do this in 3 steps. First of all, we generate synthetic examples of reasoning in a formal language. So in our case, we use Datalog, but any formal system could be used. As an example, we want to generate facts and rules and a question and answer. So for instance, we might generate the fact in our formal language, Bob is big. We might have a rule like big things are green. And then we're going to ask a question, is Bob green? And the answer to this, we can compute with a theorem prover running over the facts and rules we've generated, should be true. Second, we replace the formal statements with natural language equivalents using simple natural language generation techniques and simple templates. For example, the fact that the formal statement Bob is big is replaced with a sentence Bob is big. The rule is replaced by an English sentence, big people are green. And the question is also replaced by a statement, is Bob green? And so we can do this to generate our facts and rules and the question in an English rendition. And then just to show this for a larger theory, we have a theory generator. It's generating a collection of facts and rules automatically in a random way. We then convert those into English using templates. And then to work out the label that should go on the question at the end here, is Bob green, we'll use a formal reasoner applied to the formal theory. And so the label should be true here. And so this on the right constitutes one training example of facts, rules, and a question and the desirable conclusion if the system is indeed following a rational line of reasoning with the rules that are provided. So then the next stage is to train a model. So we run this at scale to generate thousands of training examples like this. Note that each training example has a different set of facts and rules in it. So the model sees lots of examples of how they might combine to derive conclusions. We then feed this into Roberta, and it then learns to predict the gold labels, true or false, assigned to the question attached in each of the training examples. And so now I'll describe some of the experiments we've conducted. I'll describe 3 of them. And to do this, we created 5 different data sets, each with increasing levels of difficulty. And then we trained 5 different models using these. So the first data set contains only lookup questions. In other words, where the answer is simply one of the facts that's been written down in the set of facts and rules. So you can think of this as reasoning to depth 0. The second data set has questions requiring up to depth 1 proofs. In other words, questions that require just a single rule to be applied to find the answer. The third data set has questions requiring questions up to depth 2 of reasoning. In other words, chaining 2 rules together. And then D3 and D5 data sets require significantly deeper reasoning. So D3 includes questions requiring proofs up to depth 3, and D5 requires proofs up to depth 5. These depth 5 proofs are pretty formidable to answer even for a person. They're pretty long and complex proofs. We then trained 5 different models, one for each of the data sets that I just described. And we then tested each model firstly against the test partitions for its own training data. And the results are shown here. And as you can see, the models learn to solve the new test problems almost perfectly. Perhaps the model, though, is simply memorizing some of the proof structures it's seen during training, rather than really properly reasoning in a systematic way. So to test this, we also tested the models on questions that require deeper reasoning than seen during training, to see if the models are able to generalize the reasoning patterns and answer new questions. For example, if we test the model trained on the D0 problems, the lookup questions, on problems that require deeper reasoning at depths 1, 2, 3, and 4, as you see, that model does pretty poorly. It's probably not surprising, as the system's only seen lookup questions during training. And notice these in red are out-of-domain tests. These are reasoning tests not seen during training. Secondly, if we look at the depth 1 model's performance on harder reasoning tasks, again, it doesn't perform very well. The depth 2 system is able to reason reasonably well with problems at depth 3, even though it's never seen depth 3 problems before. And when we look at the depth 3 model, we find it's able to solve these out-of-domain tasks at depth 4 and 5 almost perfectly. In other words, it's showing evidence here that training up to depth 3, the system has learned how to reason in some kind of compositional way to solve these much harder problems not seen during training time. So this is a very exciting result. The second set of experiments we did was to apply the trained model to new hand-authored rule bases. So we took a well-known logic program about birds and ostriches and flying from a textbook that's shown here. And then first we transcribed it into English, as shown here. So we have the rules expressed in English. And the question now is, given this English rendition of this logic problem and various questions and additional ones to these ones, can RuleTaker answer these problems? So we gave it to RuleTaker, and the results as shown here illustrate that indeed RuleTaker is able to answer these questions almost perfectly. And note this is 0 shot without training on these style of problems. And we conducted a similar test using rule bases about electricity circuits. And again, we see very high out-of-domain performance. Again, this is 0 shot. And then our third experiment was to test robustness to more linguistic variation. And so for this, we asked Turkers to rewrite some of the English theories into more colorful language. For instance, given a theory like this, Turkers would rewrite it in phrasing as shown here. So for example, the statement Alan is cold was rewritten as, in this particular case, in the snow sits Alan crying from being cold. And then what we did was to give these more varied linguistic renditions of the knowledge to RuleTaker to see how it performs. And what we found was, at least on the test partition here, 0 shots, RuleTaker trained on depth equals 3, performed moderately well. So it showed some robustness to this varied language, even though it hadn't seen any in training. And more importantly, if we add a small number of examples into the training set, the system rapidly learns to adapt to this varied form of language and performs again very highly on this data set. So the original RuleTaker work was performed several months ago, and I'd like to briefly mention 2 interesting follow-ups that have happened since. First of all, Leap of Thought by Alan Talmore showed that you can modify the training so that the model learns to combine explicit rules with implicit knowledge that the model already learnt during pre-training. For example, the model learns to combine the explicit knowledge that mammals have lungs with its implicit knowledge that whales are mammals to infer that whales have lungs. Secondly, the prover system by Swanadeep Saha showed how to generate proofs for answers, a step towards explanation of RuleTaker conclusions. So to conclude, RuleTaker demonstrates that transformers can learn the skill of reasoning itself over natural language rules, bypassing the need for a formal representation. It's important to know, though, that this is still not full natural language inference. Human reasoning with language includes additional things like common sense jumps that RuleTaker is currently not able to make. The work, though, does point to a new way of teaching our models, rather than giving a model large numbers of examples and hoping the system learns some generalizations from them. Instead, we can simply tell the system the general knowledge it needs, and if it can reason systematically, it'll draw the right conclusions. And if it makes a mistake, we can explore its chain of reasoning and debug its incorrect beliefs. Again, an exciting possibility that's made possible. I encourage you to try out the demo at this URL shown here. Thanks a lot.